Everyone, it's me, your journal Abedin Miah. I'm back again. So today we will be reading our research paper, and this paper is titled ImageNet Classification with Deep Convolutional Neural Network, and written by Alex, Ilya, and Geoffrey, affiliated with University of Toronto. And this paper is also known as AlexNet paper, gave rise to some of the most crucial technologies like face recognition software and also social media tagging like face tagging, also medical classification, medical reports, and lots of things. So this paper was released in 2012, gave, and this is really that time this is really a crucial paper. Also, this was on a competition on ImageNet LSRSPC 2010 competition. They took part on also the top 1, top 5 error rates. It's really great. And because of this their work, we have so many advancements in our real world. So let's check that out, what they have done. So before reading a research paper, all you have to do is go through this abstract. And this abstract will tell you what the research paper is about, and it will make you feel interested to read the research paper more. So I will leave the abstract to you all so that you can read it. So now let's go through the first introduction of this paper. So let's start it. So first they're telling us the current approaches to object recognition make essential use of machine learning methods. So you can see we can highlight this one. So you can see the machine learning methods were also used at that time, like we are also using it now, and it also helps us detect objects. To improve their performance, we can collect larger data sets, learn more powerful model, and use better technique for overfitting, preventing overfitting. Until recently, datasets of labeled images were relatively small, on the order of tens, thousands of images. Nor 16 Celtic 101 by 256, 89, and C410 by 200, which was really small dataset, and simple recognition task can be solved well with the data of this size, especially if they augmented with label preventive transformation. For example, the current based rate on the MNI's digital recognition task was less than 0.3 person approaches human performance flow. So yep, you can leave that out. Then also let's mark the new larger dataset included label me, which consists of hundreds of thousands of fully segmented images, like ImageNet, which consists of over 15 million label high resolution images in over 22,000 categories. You can see how large dataset this was. And this was really a challenge test, like 15 training of 15 million label high resolution images wasn't possible. Except now we are using GPU, so they also use GPU here, but it was really large data sets, like 15 million label images. Can't imagine how much time it will actually take. Also, to learn about thousands of objects from million images, we need a model with large learning capacity. So they needed a model with large capacity. We can mark that out. However, the immense complexity of the object recognition task means that this problem cannot be specified even by dataset as large as ImageNet. So our model should also have lots of prior knowledge to compensate all the data we don't have. So the model is to compensate all the data they don't have, and they can compensate with CNN, as stated by here. The CNN constitute one such class of models, and their capacity can be controlled by varying depth and breadth, but they also make strong and mostly correct assumptions. So they're justifying that they're using the CNN for image just like on that time, nobody actually used CNN for image classification. No one actually knew that how to use CNN for image classification. So they're justifying that why they're actually using CNN for this task. So yeah, about the nature of the image claim stationary of statistics and locally of pixel dependencies. So their capacity can be controlled by varying their depth and breadth, and they also make strong and mostly correct assumptions about the nature of images, namely stationary, statistics, and locally of pixel dependencies. So you can see how good CNN is for image classification. We are actually on this day we are actually using CNN to train our images, but we actually don't know where this actually came from, and this actually came from this paper for the work that Alex did with his teammates. Also, you can see the how large the data set they trained on, like 15 million high resolution images, and also the 20,000 categories. So many categories. You can't imagine how many categories that they have to train on. It will take like weeks and weeks, but because of the GPU, it took less time for them, like 6 days or so. Now let's go through the rest of the paper. So despite the attractive qualities of CNN and despite the relative efficiency of the local architecture, they have still been prohibitively expensive to apply in large scale to high resolution images. Luckily, current GPUs paired with highly optimized implementation of 2D convolutional are powerful enough to facilitate the training of interestingly large CNNs. And recent datasets such as ImageNet contain enough label examples to train such models without severe overfitting. You can see that overfitting was also really crucial at that time. Like they also used to face issues like overfitting, which we all sometimes face now. But the overfitting has, I think now we don't much face this overfitting issue, but at that time they used to face this overfitting issue as well. And they also use several approaches in this paper to overcome the overfitting. And we will check that how they actually deal with the overfitting issue here. They also use the data augmentation technique here to so that to overcome this overfitting issue. Also dropout as well. Now let's go through the paper. So the specific contribution of the paper, such as follows, we trained on one of the largest combination neural network to date on the subset of ImageNet used in the ILS BRC 2010 is the competition name, and also ILS BRC 2012 competitions achieved by far the best results are ever reported on these datasets. So yeah, they also got the best error rate here on this competition. You can see the results here. You can see the how better the model performed in this competition, 37.5 to 17% top 5, which is really great here. Also from 45% here to 25.7%. Now let's go back here. We wrote a highly optimized GPU implementation. So they use GPU implementation of 2D convolution and all the other operations inherent in training convolution neural network, which we make available publicly Our network contains a number of new and unusual features which improve its performance and reduce its training time, which are detailed in section 3. We will go through that. The size of our network made overfitting a significant point. This overfitting was the problem that was there even with 1.2 million label training examples. See, even with so many large datasets, we also had faced overfitting. So we use several effective trainers for preventing overfittings. So there is several overfitting to overcome this overfitting, as we have discussed. Our final network contains 5 convolutional and 3 fully connected layers. So there is 5 layers and also 3 fully connected layers, like 3 layers connected to each other. 5 layers actually gives the depth. You can see the and this depth seems to be important. So we found that removing any combination layer, each of which contain no more than 1% of the model's parameter. So you can see if you remove one layer from this, the you will see that the model will it will affect the model more. Like 1% is such huge, resulting in inferior performance. In the end, the network size is limited mainly by the amount of memory available on the current CPU and by the amount of training time that we are willing to tolerate. So GPU was really crucial for speeding up the training process. You can see that JBL GTX 580 3GB GPUs, which is compared to this, they not so large enough because we have now larger GPUs like RTX 5000 series and lots of GPUs available now. But they had to use 2 GPUs for this. And because of the GPUs, the training time reduced to 6 days. Like if they didn't use GPU, it would take so many weeks. And they wouldn't have used it on the competition if the training would take like weeks. So all of our experiments suggest that our results can be improved by simply by waiting for faster GPUs and bigger dataset to become available. So it also be improved by adding more datasets when the bigger datasets are available or faster GPUs. So you can see the image is large datasets like 15 million label high resolution images belonging to so many large categories here. And you can see that there will also be 50,000 validation images, 1,000 image in each 1,000 categories. So many categories here. We can mark it out. Also 150,000 testing images. This was for testing. 1.2 million in training units. So you can see that they use large data sets for training. Also on 1,000 categories. So it needed GPU. Without GPU, training would have taken so many weeks. Also 150,000 for training testing images. And you can see that they have also a top 1, top 5 error rate is a fraction of test images for which the correct label is not among the 5 labels considered most probable by the model. ImageNet is considered the variable resolution images while our system requires constant input dimensionality. Therefore, we downsample the image to a fixed resolution of 256 to 256. You can see that they've downsampled it to this size. Like this was really great job, Alex. Like really crucial. How hard they had to work. On that time, there's no TensorFlow. Also, now we have GPT, ChatGPT, and lots of TensorFlow, lots of research available. And on that time, they didn't have like, any TensorFlow or anything. They had to work all alone by themselves, hardcore, all alone by themselves. So you really can imagine how much work they have put on here. Really hats off to them. rectangular images. We first rescaled the image such that the shorter side was of length 256 and then cropped out the central to 256. So they cropped the length to 256 and 256. From the resulting images, we did not reprocess the image in any other way except for subtracting the mean activity over training set from each pixel. So we train our network on center raw RGB values of the pixels. So yep, that's data sets. Here are all the details about data sets. Now let's go to check out the architecture. The architecture is telling us that on figure 2. So this is the architecture. Let's see. So this is the architecture that they worked on. You can see that this is an illustration of the architecture of our CNN, explicitly showing the delineation of responsibility between the two GPUs. You can see that two GPUs. Also, they use max pooling here. You can see max pooling. Also, the max pooling is also used here. On that time, they also use max pooling. You can see that max pooling are also here. Let me just change. Also, you can see that here they're connected layers here, connecting. This one is connected to this one is connected to this, also so on. You can see how dense the layers are. Also, between the two GPUs, one GPU runs the layer parts of the top of the figure, while the other runs the layer parts at the bottom. The GPUs communicate only at certain point. You can see how the trick between the GPUs like only they have only communicate at certain point, but before that they don't communicate. Like they communicate only when they're needed, and after that they check whether the answers are correct or not. Like for example, me and my friends are giving tests, and our teacher asked us to do the task on our own. So we are doing all our own. Then at starting point, teacher tell us to now group discuss with each other and see who got the correct. And then we discuss with each other and see that if we got the answer correct or not. Then we discuss. Then our teacher tells us again. Now up back to another question. Then also so on. So this is the trick that Alex has used, and so hats off with them. The team they put so many work on here. Also, the GPU's coming at certain point. The network's input is 150,528 dimensional, and the number of neurons in the network's remaining layer is given by 253 to 1,000 to 440 and so on and so on. We don't have to read that. You just can read if you want. So the overall architecture is here. You can see that. Also, there is ReLU non-linearity. This is crucial because ReLU is because what do you mean by ReLU? We mean by restrictified linear units, and this was really crucial for speeding up the training process. Why is it? Because this was a standard. So let's go through the section 3.1. The standard way to model a neuron's output f as a function of its input x is with f of x equals to tan h of x, which was hyperbolic x, or f of x equals to 1 plus. This is the equation here. In terms of training time with gradient descent, this saturating nonlinearity are much lower than non-saturating linearity. F of x max 0x. So you can see the how slow this training was. Like before this paper, Dave is used to use this like hyperbolic functions, which is it takes so much time. Let me show you on the graph. Like for example, you have seen like we have studied biology. Like in biology, we have neurons, we have dendrites in the neuron, which transfers information to us, and some of those transformation. But let me just show you that. Give me a couple of minutes. I think my pen is exhausting. So, so they're saying that, so previously, before this paper, they've used like, they've described like neurons as biological neuron. Like on biological neuron, we have the dendrite, then also all the network signals sends here to dendrite, and sums of all of those are goes to the like action potential of something. Like for example, on the graph, we can see that the graph is spikes here, but it's hard to calculate grading distance from here. So you can see it's really hard on the from the graph to calculate grading distance here. Also, you can see that using this equation, are getting this curve, which is really like 6 times less than the what we're getting on really. This one is the result given by the ReLU. Also, we are using this rectified linear units. ReLU still now. So let's put this out. So in terms of training time with gradient descent, the saturating nonlinearities are much lower than non-saturating nonlinearity f of x minus x. Following Miah and Hinton, we refer to neurons with this nonlinearity as rectified linear units. ReLU's give convolution neural network works with ReLU trained several times faster than their equivalent hyperbolic 10H units. So you can see how they're working faster, how this is ReLU is working faster than the 10H units are. This demonstrated in figure 1 here, which shows that number of iterations required to reach 25% training error on say per 10 datasets for a particular 4-layer convolutional neural network. This plot shows that we would not have been able to experiment with such larger network for this work if we had used like traditional saturating neural models. So ReLU has made this training much more faster than it was before. So they use ReLU and justified why they use justified linear units. We also use justified linear units still now, like they've used Euro, and also they're saying why they're using training on multiple GPUs and how they're using it on 1.2 million training examples are enough to train networks which are too big to fit on one GPU. Like it was so big to fit on one GPU, so they're using two GPU. The current GPUs are particularly well suited to cross GPU parallelization, so as they're able to read from and write to one another's memory directly without going through host machine memory. The parallelization scheme that we employ essentially puts half of the kernel or neuron on each GPU with one additional trick. So they're using the trick, and the trick is the GPUs communicate only in certain points. So as I've told you, like for example, you have an exam and your teacher asks to do solve a question on your own. So you and a friend are asked to solve a question on your own, and you are allowed to communicate at certain time, then we communicate a certain time and discuss with each other. And after that, your teacher tells you to solve another question all alone, and also then tells you to communicate a certain time. And this is how the GPS is working here. This means that, for example, the kernel of layer 3 take input from all kernel maps in layer 2. However, the kernel in layer 4 take input only on those kernel maps in layer 3, which reside on the same GPU. Choosing the pattern of connectivity is a problem for cross-validation, but this allows to precisely tune the amount of communication until it is acceptable fraction of the amount of computation. So you can see the error rates here, how the GPU have increased the model potential. Like error hash rates have decreased so much, like 1.7 and 1.2 respectively, as compared with the net with half as many kernel in each combination neural network trained on one GPU. The two GPU nets take slightly less time to train on one GPU net. So two GPU net was really crucial for their improvement. As also you can see the equation here.
So now let's talk about local normalization, response normalization. So what is this? For example, imagine a team of tiny word pairs. We can imagine a team of tiny word pairs, and we call them neurons. So let's say they are neurons. Look at this out. Neurons, 15 neurons. So they're the tiny word pairs. Sorry, it's taking some time. Neurons. Oops, let's pop out a page. So let's say the team of workers are neurons, and when one of them get excited, like this one, like this is the smartest one, and these neurons get excited and it shouts. So like it shouts a number that I see a huge ace too loudly, and the other who are also got dancers, but they can they cannot speak out loudly because of this one neuron. So this affects overall performance of the neuron. So if one of them get excited and speaks loudly, others gets other doesn't get confidence, like humans. For example, in our class, if one is brilliant and speaks out loudly to his teacher, the other students who knows the answer but can openly answer because of the other neuron. So what the local normalization does is it actually balances things out. Looks at each neuron and checks how excited its neighbor makes are. If the neuron is way more excited than its neighbor, its local normalization calms it down. Like don't shout loudly. So this creates a little competition. So all neurons work together and focuses on different parts of the picture. So think of it like you are heading out of your house in a sunny day and you see a bright sun, and then your eyes shrink. Why? This is how the local response normalization actually works. rise string because of the bright sun, and local response normalization string, and local and localization string the over confident one. So yeah. So this is the formula of the local normalization, and you can see that whenever it's get loudly, it's denoted by this one, alpha, and yes. So let's read it out. So while the sum runs over n adjacents, kernel max at the same partial position, and n is the total number of kernels in the layer. The ordering of the kernel map is the course arbitrary and determined before training begins. This sort of response normalization implements a form of lateral inhibition inspired by the type of found in neural neurons, creating a competition for big activities among neuron values are determined by using validation. We used k equals to 2, n equals to 5, alpha equals to 10 to 95. We apply the normalization of curve, applying the real non-linearity. So they applied this normality, nonlinearity. You can see the nonlinearity. So they applied this one. Then certainly the scheme bears some resembles to the local contrast normalization scheme. And you can see that how much it affected, like the response normals reduces our top 1 to top 10 years by 1.4 to 1.2% respectively. So you can see how this affected. We also verify the effectiveness on a small dataset. So they also tested on small datasets. The 4-layer CNN achieved the rate like 13% test rate without normalization, 11% with normalization. So you can see the difference. This is a huge difference. Now let's talk about overlapping cleaning. So it's like a pooling layer in CNS summarize the output of neighboring groups of neurons in the same kernel node. So for example, let's say looking just super well. So let's say we have this. Like overlapping pooling is like this. Just square. So this is like overlap. This is like the normal pooling. So normal pooling would actually look like this. Then let's out of this out. Let's move to 3. Everyone joins. So overlapping to search. What is the pooling actually is? So let's say for example, oops. Let's say for example we have this pooling and there are small squares in a picture, or small circles, and this is like 2 into 2 box. So from each box, the boxes don't overlap like this. Circles here it doesn't overlap with each other. But on overlapping pooling, we have on this paper, it overlaps. Like for example, this overlap with each other. So what it actually does is, while overlapping, it's reading the same thing twice. For example, we are reading a comic book, and if we read the same paper, same page 2 times, the page we will read, then we'll actually get idea of the what this comic book is all about. So this gives us the clear picture without memorizing. So overlapping pooling does is it helps us not to memory, but get idea like what's this paper about. Like we read the same thing twice, so modern don't actually forget that what actually the we're dealing with. So let's read this out. Pooling layers in CNN summarize the output of neuron groups of neuron in the same kernel map. Traditionally, the neighborhood summarized by adjacent pooling units do not overlap. Let's see the number. To be more precise, a pooling layer can be thought of as consisting of a grid of pooling units spaced as pixels apart, with summarizing a neighborhood of size sites like this one, that is 2 into 2 and 3 into 3. Centered allocation of the pooling unit. If we set S equals to 2, S equals to Z, we obtain local pooling. Like if they both same, like S, the pixel size, uh, the pixel apart and Z size are same, we just do this normal pooling, 2 into 2 pooling. So we obtain traditional local pooling as commonly employed in CNN, which we set as local left, like if this one is low than fifth, literally. So this is applied when S equals 2, it's like equals to Z, and this one is applied when S less than Z. S is the size apart and the Z is the center location. So this is what we use to throughout our network. With S equals to 2 and Z equals to 3, one is bigger than another. This scheme reduces the top 1 and top 5 error rate by 0.4% and 0.3%. You can see how much difference it's making. It's 0.3% and 0.4%. How the error is made. Let's mark it out. So you can see then how it for deep is the as compared with non-overlooking scheme. Non-overlooking didn't perform that well, which produce output of output equivalent dimension. We generally observe that during training that models with overlapping pooling find it slightly more difficult to overfit. So you can see if you read a common book twice, you don't actually overfit. Like you don't forget what you have read. For example, if we memorize a book, we actually sometimes forget like what was it about. But when we don't memorize, we try to understand. Like we read the same book twice and understand the whole picture. We actually can answer any question. Like if the question is out of the book, or then we can also answer our question. So yeah, it's like that. So here, this helps us to prevent overfitting here. Now let's read next step.
So you can see how much depth they have to go to fix the overlapping issue. And this is where we discuss the overall architecture. Let's see the architecture here. An input image of 96 kernel size scale. And also reducing overfitting. So their neural network architecture has 60 million parameters, all through 1000 classes of ILS make ILS make each training example impose 10 bits of constraint on the mapping from image to label. This turns out to be insufficient to learn so many parameters without considerable overfitting. Below we describe the two primary issues in which we combat overfitting. So overfitting is like the issue. Like for example, the training is during training they see that the model is performing really great. Like model is giving us really good result, but after validating the results, you can see that it's actually cheating. Like it's not knowing what this. For example, we give it a picture of dog, it says that it's not dog, it's cat. So this is what overfitting does. Okay. It's like cheating, like memorizing for your exam, then giving an exam without understanding what the exam actually is. The easiest and the most common method to reduce overfitting an image data is to artificially enlarge the dataset with augmentation, using label preserving and transformation, sequencing data augmentation as helping here for overfitting issues. We employ two distinct forms of data augmentation, both of which allow transform images to be produced from the original images with very little computation. So the transfer image do not need to be stored on disk. In our implementation, the transform images are generated in Python code on the CPU while the GPU is training on the previous batch of images. So the transform images are actually generated in the Python from CPU, like they have separately generating the images on the another CPU while GPU is handling another task. So this data augmentation schemes are in effect computational free. So that also computational free, which is great. The first form of data augmentation consists of generating images translations and horizontal reflections. We do this by extracting random 22 for patches and the horizontal restrictions, like they're rotating the images and then turning it. And they're also rotating this way, like they enlarge the images and turning it on the network. On this extracted patches, this increases the size of our training by a factor of 2048. So the resulting training examples, of course, highly interdependent. Without this scheme, our network suffers from substantial overfitting. So without this scheme, data augmentation, there's augmentation is overfitting issues. So data augmentation actually helps. Like for example, if we if we tell a child, like if we show a child a picture of dog, then we change the color of the picture. Like for example, we change the color of the picture, then we train our child with it. The child will actually know that if this is a dog because they were all already knows through training like it's a dog or not before. So while testing, it will actually know that if it's a picture of dog or not. So overfitting helps us like train the if suppose if you're trained with large data sets that's contain so many images, same images with like rotating reflection and also so on, then you will actually get in your head that what that picture actually is. The four corner patches and a center patch as well as the horizontal reflection. So as you can see reflections are also used. Hence 10 patches in all, so 10 patches for all. Averaging prediction made by the network softmax layer on the 10 patches. The second form of data augmentation consists of altering the intensities of RGB. So they also use RGB, like changing the color of the image training images. Especially we perform PCA on the set of RGB. So they've also used the principal component analysis on the set of RGB pixel on the set of RGB pixel values throughout the ImageNet training set. So to each training images, we add multiple of the found principal component. This is the reason why the input image in figure 2, let's check the figure 2. Let's see the figure 2 here are 224. So the dimension of this is 224 because of this. Three dimensional. So as you can see here, Also, you can see the equation here. Now let's go to dropout. So combining the predictions. Also, before that, let me just show you the how data augmentation has increased, has decreased the error rate. So this still reduces the error rate, top one error rate by 1%, which was really crucial here. We have to remember this one. So combining the prediction of many different models is a very successful way to reduce test errors. So data augmentation was also great, but here dropout, what dropout does is, for example, we have a football team, and on football team, one is really great player, and if you pick that player for like, if we play that player, and if the team is dependent on that player, the other players will not get perform really well. So what the coach will do is, coach will drop the player out, like the player which is playing great, and give the other player chances to play. So everyone gets the chance to be the superstar of their team. So in that way, this is the dropout does. Dropout actually drop, drops those overperforming neurons, then let the other neuron do the work, like dropping half of the neurons and let the other half perform. So let's read that out. Combining the prediction of many different models is a very successful way to reduce test error, but it appears to be expensive for big neural network that already takes several days to train. There is, however, a very efficient version of model combination that only costs about a factor of two debugging during training. The recently introduced technique called dropout consists of setting to zero the output of each hidden neuron with probability of zero point 0.5. So hidden neurons with zero point 0.5 probability was also set to zero. The neurons which are dropped out in this way do not contribute to the forward pass and do not participate in back propagation. So those which were negative were set to zero so that they don't interact while training those who are performing really well. So every time an input is presented, the neural network samples a different architecture, but all these architectures share weights. So they all share same weights. This technique reduces complex coadaptation of neurons since neurons cannot rely on the presence of particular other neuron. So neurons cannot rely on one neuron only, or other neuron only. They have to rely on themselves. It is therefore forced to learn more robust features that are useful in conjunction with many different random subsets of the other neurons. At this time, we use all the neurons but multiply the outputs by 0.5, which is reasonably approximation to taking geometric mean of the predictive distribution produced by the exponentially many dropout networks. With dropout in the full first fully connected layers. Without dropout, our network exhibits like substantial overfitting. So without dropout, we actually take the overfitting issue again. Dropout roughly doubles the number of iterations required to converge. So it also doubles the required to converge here. And also this line is crucial. Without dropout, our network exhibits substantial overfitting. So you can see how many steps they had to go through to fix the overfitting issue. Also, in my district, I also face this overfitting issue. Like sometimes the overfitting issue really quite disturbing, but hopefully with this solution, you can go through the overfitting issue. Now our advanced techniques are, there are lots of advanced technologies here, so we can cope up with the overfitting issue really well. So details of learning, we train our models using stochastic gradient descent with a batch of 120 examples, moment of zero point 0.9 and weight decay. So They use this batch size, momentum, and also with decay. Batch size is really crucial. Like without batch size, you don't know which how many times you have to go through. Also, momentum keeps you going. Also, we have weight decay. We found that this small amount of weight decay was important for the model to learn. In other words, weight decay here is not merely regularizer, it reduces model training error. So it reduces the error. The weight decay is very crucial here. It actually reduces the error that your training will face. And this is the equation here. We initiate the weights in each layer from 0. Mean Gaussian distribution with standard variation with 0.01. We initialize the neurons bias in the second, fourth, and fifth convolution neural network as well as in the fully connected hidden layers. So fully connected hidden layers with the constant 1. The initialization accelerator in the early stages of learning, providing the value with positive inputs. We initialize the neurons biases in the remaining layers with a constant 0. And we use an equal rate for all layers, which we adjust manually throughout the training. So we follow was to divide the learning rate by 10 when the validation error rate stopped improving with the current learning rate. The learning rate was initialized at the 0.01 and reduced to 3 times per determination. We trained the network for roughly 90 cycles throughout the training set of 1.2 million images. So because of the GPU, it takes so many less time. Also, they have to 90 cycles to each 1.2 million. So you can images. You can see how many times they have to cycle this training networks. And you can see the results here. See how would the model actually perform. Like error rates decrease so much, like 17% here. This was really crucial. Our results on ILS BRC ImageNet competition, which was named as ILS BRC 2010, are submitted in table 1. See on table 1 the results here. Our network achieves top 1 and top 5 set their tester set error rates of 37.5 and 17.0%. The best performance achieved during ILS BRC 2000 competition was 47.1 and 28.2%. On 2010, its results severe with an approach that averages creation produced from sparse models trained on different feature scenes. The best published results are 35.7%, 25.7% with an accurate average separation of two classified trained on feature vectors, computed with two types of density layer samples features. Sequence densely there be extensive sample feature vectors, these are the feature vectors. We also entered our model in the ILS DRC 2012. So they, after 2010, we also took part on 2012 competition and report our result in table 2. So you can see the 2012 competition results. So you can see how much really they have got, like 15.3 from 70% to 15.3, which was really crucial. And because of this, the technology become more modernized today now because of their work. We cannot report the test error rates for all models that we tried. In the remainder of this paragraph, with validation test error rates interchangeably because in our experience we do not differ by more than 0.1%. Frequency more than 0.1%. Established. The CNN display in this paper achieves the top 5 rates. CNN was really crucial for this training. 18.2%, averaging the variation of 5 similar CNNs, given error rate of 16.4%. And also you can see that training with an extra six convolution neural network over the last pooling layer to classify the entire ImageNet for 2011 release 15 million images to 22,000 categories, and then fine tuning it on wireless BRC gives an error rate 16.6%. Look how the model have improved from previously to that because of the changes on CNN. So you can see here. You can also go through this here. If I go through this, it will take so much time. I don't want to take so much time for you. So our top 1 and top 5 error rates on this dataset are here, 16.4, 7.4. So you can see that how the model performed really well. The blessed results are the 78.1% to 60.9%. So you can see also they evaluated qualitatively. So you can see that here on figure ones here. 8 ILOs BRC 2010 test images and the 5 labels considered the most probable by our model. The correct label is written under the image. So you can see the label. So how well the model detected here, also here, also here. So you can see how the model is performing really well here. And guessing here it got incorrect, here it got incorrect. The correct image is written under image and the assigned to the correct label is also shown with red bar. If it happens to be the top 5, on the right you can see top 5 ILS 2010 test images in the first column. So on the first column is 2010 images, 2010 competition images. Okay. Remaining column shows the 6 training images that produce feature vector in the hidden layer with the smallest resolution distance from the feature vector for the test images. Our results show that a large, deep convolution neural network. So you can also read that here, quality evaluation here. We can go to the discussion now. So our results show that the large deep convolution neural network is capable of achieving record-breaking results on highly challenging dataset using purely supervised learning. So with there is supervised learning here, it is notable that our network's performance degrades if a single combination layer is too. So if you know the single layer, it will perform really poor. For example, remove any middle layer results in a loss of 2%, which is crucial for the top 1 performance of the network. So the depth really is important for achieving our results. So depth was really important. To simplify our experiment, we did not use any unsupervised learning. So if you want, you can also use unsupervised speed training. There are also room for improvement, like in this line, they're showing the improvement that the model is required for future research. Even though we expect that it will help, especially if we obtain enough computation power. That time, the computation power wasn't available. To significantly increase the size of the network without obtaining a corresponding increase in the amount of level data, tests for our results have improved as we have made our network larger, trending on longer, but we still have many order to magnitude to go in order to make the infer temporal pathways of the human culture systems. Also, in this paper, they didn't use any videos here, like videos of dog running or cat running. So if they use videos for detection, they have also gotten really good performance here. Many order of magnitude to go in order to match the infer-temporal pathways of the human culture system. Ultimately, we would like to use large and deep convolution nets on video sequence. So you can see there also have a video sequence where the temporal structures provides very helpful information that is missing or far less obvious inside of images. So these are this paper. So, so I hope you guys have really enjoyed learning about this paper. I don't know how much I was able to go through the paper. Like, I know how boring it is to just read paper and really go through all of that. Also was like our first time out before reading this paper, I was actually bored. But then when I understood this paper after reading the whole fully and understanding the depth of it, I actually got to know lots of about it. And it actually made me realize like how much this paper has worked. Like for their work, we are getting with so many advanced technologies, your face recognition, so many tasks.